Hi, this is Riley. Today I'm going to be talking about exomoon detections and transit light curves. And I'm going to be talking about the paper published by Kai Rodenbeck, Renee Heller, and Laurent Gizon earlier this year on April 5th, called Exomoon Indicators in High Precision Transit Light Curves. So first we're going to talk about the definition of an exomoon. And it's quite simple. It can be defined as a natural satellite that orbits an exoplanet. And it's inferred from the study of natural satellites in our own solar system that exomoons are common in planetary systems amongst the universe. And despite recent discoveries, including evaporating planets and exocomets, we still haven't quite been able to detect an exomoon. So as of right now, it's only theorized. However, we've detected numerous exomoon candidates with a variety of interesting methods, including direct photometric observations of exomoon transits, scatter analysis of average light curves, gravitational microlensing, pulsar timing observations, and many more. So now we're going to get more into the paper. And the paper goes over a specific method for exomoon indication. So for the purposes of this presentation, we're going to be talking strictly about transit light curves. And the paper we're using was published very recently. And the goal of the paper was to provide the exoplanet community tool to observe light curve distributions for exomoon candidates without the need to meticulously develop a fully consistent transit model of an exoplanet with an exomoon. And in the paper, the authors compares variations within transit data for an exoplanet-only system and a planet-moon system. And going further into this, they do this by looking for transit timing variations, transit duration variations, and transit radius variations. Transit timing variations come from when a planet leads or trails the planet-moon system's barycenter, with the planet-moon axis oriented perpendicular to the line of sight. The transit duration variations come from when the planet's motion along the path of the transit relative to the system's barycenter, with respect to the moon-planet axis oriented along the line of sight. And the transit radius variations come naturally as a result of transit depth fluctuations found in exoplanets, but this concept hasn't really been applied to exomoons before this paper. And yeah, this paper is really, to them, is really important for future exomoon detections because it kind of goes over the effectiveness of previous exomoon detections, including previous methods with the transit timing variations and transit duration variations. So first, before we dive into the results, we're gonna go into the basic exomoon evidence, which is just this basic plot that they provided in the paper that basically shows transit depth, or pardon me, a transit light curve of an exomoon passing in front of a star. And we can see that there's this extra dip at the bottom of the light curve, which kind of indicates that an exomoon exists. But there are various explanations to why this could happen. And as a result, we only have candidates, and we haven't really conclusively found one specific exomoon yet. Okay, getting back to it. Also in this exomoon evidence plot we have here, we also see two visible TTV effects that can be inferred from this plot. One of them comes from the additional dimming of the star by a sufficiently large moon, which shifts the photometric center of the combined transit. And the other TTV effect comes from the fact that the midpoint of the planetary transit changes between transits with respect to the planet-moon barycenter. And now we're gonna, before we go into the evidence, it's also important to note that during these transit light curve simulations. The authors implement multiple realistic conditions in their simulations, including stellar limb darkening, and orbital inclinations, planet-moon occultations, and noise from both stellar granulation and instrumental effects. All right, so now getting into the first part of the results. This figure shows simulated transit light curves for TDV effects, which is shown in, which is labeled A, TRV effects, which is labeled B, TDV effects, oh, pardon me, TDV effects is A, TTV is B, TRV is C, and the D plots are the combined effects for the TTV and the TDV. So D is a combination of A and B. This simulation shows us signatures of exomoons and exoplanet-only transit model fits. This is important because these models infer only an exoplanet system. So this is without the presence of a moon. And so for each of these panels, we can see that they're separated into 3 subplots. The first of these subplots on the top is the photometric distortion due to the moon. The second of these subplots are the barycentric motion of the planet due to the perceived moon. And the third is a combination of these 2 effects. And one important thing to note for the rest of these plots are that the orange lines represent a system that is has no occultations, and the blue system refers to a coplanar planet-moon system, which is a system with occultations. And that's going to be important because the remaining plots, besides the periodogram, is going to have these 2 different lines. And it's also important to note that for these simulations, that all panels assume a Jupiter-sized planet with a period of 30 days around its sun, and an Earth-like moon with a period of around 3.5 days, similar to that of Europa. Okay, so next, we're going to look at the TTV and the TDV, and also the TRV effects of the Earth-sized moon around a Europa-sized orbit of the planet. So this is including the exomoon. And these plots are separated with as noise over here on the left, and noise simulating, I guess, instrumental noise and basic noise that could be found in Plato, which is a mission that's set to launch in the future, I think around 2026. That's kind of like a surveying mission, sort of like Kepler. Oh, and it's also important to note that these observations with the noise assume a star with a bright magnitude of around 8. So these stars are assumed to be very bright. Okay, so in these plots on the left, we can kind of see a sort of periodic fluctuation here. And to get a better understanding of the periodicity of these functions, of these distributions that we're seeing in the light curves here, it's pretty useful to represent them in terms of periodograms. And so that's what these plots on the right here are. And these are directly correlated to each other. And so this plot here is the periodogram of this plot here, and so on and so forth. And what the important thing to see from this plot is that we have the most pronounced signal from our TRV observations, while we can see from the TDV and the TTV observations, it's much more sporadic and harder to get a read. And it's important that we get a strong signal for the periodicity, because this kind of gives us a stronger evidence that an exomoon might exist around these transiting exoplanets. Okay, so now we have these plots that kind of show that the TRV signal is more pronounced than the other two signals, the TTV and the TDV effects on the transit depth for the exoplanet orbiting a star. And because of that, the paper then goes on and focusing solely on the TRV effects on the exoplanet, simply because we're getting a stronger signal from it. And so that's what these next set of plots kind of go over, where these plots are simulating various instances, or I guess various types of systems with different masses and orbital radiuses, radii, and they kind of show us sorry, I lost my train of thought there. So these plots show us the different types of TRV curves or effects that we can expect from these different conditions. And they're organized accordingly. So they have just the basic TRV curves on the left here. Then they have the autocorrelation in the middle. And then they have the periodogram of the curve of the left on the right over here. And then from here, we can go on to our discussion. So some important points that they make from these plots are that systems without occultations give more sinusoidal data. And that can be seen from this first plot here, the first plot shown in the results. And basically what that means is that these orange plots here are giving stronger signals. And that's important because when you get a stronger signal, you get a higher peak in the periodogram, and you'll just get a more accurate, or I guess more effective reading of exomoon evidence. Another important conclusion that the authors of the paper came to is that the paper proposes that TRV signals improves over the course of numerous transit observations. Essentially what that means is that the more time we get to observe these TRV signals, the greater signal we should get overall. And so the longer we are observing TRV transits, the greater our evidence towards exomoon should be. So in addition to these conclusions about how we could get stronger signals and stronger evidence towards an exomoon detection, the paper also importantly notes that we have to include, or I guess note, the stellar properties of the host star to improve TRV detection rates. And this is because variations on the star's surface, such as sunspots or flares, can contribute to variations in planetary radius. And so it is best for us to consider the stellar properties of stars so we can get the most accurate light curve models. Perhaps the most important result from this paper comes from this figure right here. And when we observe the contributions of the photometric distortion and the barycentric movement outlined in this figure, we can see that in some cases that they kind of cancel each other out in the TTV and the TDV instances. And this is important because this tells us that for low density moons, the photometric distortion dominates, while for high density moons, the barycentric motion is the strongest. So in the case of exomoons, only high density moons will be able to be detected this way, essentially, since they'll still be able to produce a visible TRV curve. But in the case of low density moons, that curve is going to be obstructed by photometric distortion. And this result is really interesting because it tells us that the previous TTV and TTV-TDV methods that we've been using the past couple years may not be as effective as we thought, um, because previous methods described uh, the TTV relationship and distribution as an ellipse, as just like a simple relationship between each other. But in reality, it seems like it's much more complicated than an ellipse. And due to this interference between TTV and TDV counterparts. And this is kind of seen by the canceling out in these simulations here. So to conclude, out of all the variational transit methods within the transit light curve detection for exomoons, it seems as though observing the transit radius variations as opposed to the transit timing variations and the transit duration variations, the TTV and the TDV durations, um, of an exoplanet is more effective in detecting exoplanet candidates. And this is because the previously thought TTV, TDV methods may not be as effective as initially thought due to the interference of the photometric distortion and the barycentric motion of the moon planet system. Um, However, we still need more advanced technology in order to get more substantial evidence for the existence of an exomoon. Even though the TRV method seems like it's a great method to try to detect exomoons, um, it's still not precise enough to get an accurate measurement. And there's still other uh, properties of the system, including stellar properties of the sun, limb darkening, orbital inclinations, and other conditions that will kind of impede our ability to detect exomoons. Um, so to me, the results of this paper are pretty believable because the careful attention that the authors used in their simulations. I feel like they used a lot of conditions and a lot of various ways to try to most accurately simulate what an exomoon transit would look like. And I feel like their data and their, especially their periodograms are very telling. And I feel like their method should definitely be used in the future for exoplanet detection. And so hopefully we'll see the first detection of an exomoon soon. Um, and hopefully the most people will see that looking at the transit radius variations within transit light curves of exoplanets might be the way to go in detecting exoplanets. So thank you for listening. Uh, Here are my references I used. And the paper is going to be the first reference here. And the rest of these are all very good articles that I would recommend checking out.